Everybody, this is Professor Monty. We are jumping into chapter 13. Now we're only going to be doing 13.1 and 13.2. 13.3 is contingency tables. We've already done those in chapter 4, so we're not going to do them again in chapter 13. So 13.1, it's called the chi-squared distribution, and it's pronounced chi, like K-I, not chi. So the chi-squared distribution, and I gave you a picture out of the book what the chi-squared distribution looks like. And so it's going to look like one of these curves, and it changes depending on what we call the degrees of freedom, the DF. So we see 3 different chi-squared curves there, and let's read a little bit about their properties. So 1, total area under the chi-squared curve equals 1. That's any density curve. Property 2, a chi-squared curve starts at 0 on the horizontal axis and extends indefinitely to the right, approaching but never touching the horizontal axis. So notice this one starts at 0, doesn't go to the left, starts at 0, and then goes off to the right, which is why it's right skewed, which is property 3. A chi-squared curve is right skewed. And then property 4 is the number of degrees of freedom become larger, chi-squared curves look increasingly like normal curves. So look at that last curve with degrees of freedom 19, that's starting to look very much like a normally distributed curve. So we're going to take that. That's all that I'm going to cover in 13.1. The reason is the rest of the section just talks about how to read the chart to get the chi-squared values. We're not going to be reading the chart. We're just going to be doing the hypothesis tests in the next section using the p-value approach. So let's jump into that next section. And so it's the chi-squared goodness of fit test. So when would we use this test? Well, what this test is, it is an extension of inferences. Instead of inferences, let's say hypothesis test. So it's an extension of hypothesis testing for 2 population proportions. So we did this last time, but what we're going to do is this is an extension. So if we have 3 or more categories that we want to look at, so we'll say used for 3 or more categories, compared to some known distribution. And in fact, the degrees of freedom that they're talking about is C-1, where C equals the number of categories. And so when we do some problems, you'll see what I'm talking about in terms of categories and all that. But that's what's happening. So remember, it's an extension for population proportions. Remember, that's used for qualitative data, not quantitative data. So this is typically non-numeric data used for qualitative. Remember, that just means not numbers. We'll say non-numeric. And they do tell us in the book that it may be used for quantitative discrete. But it's more often used for qualitative. Sometimes they call it categorical. It's the non-numeric data. So that's what we're going to be using this for. So we already talked about the degrees of freedom is C-1. There's something that we talk about, the expected frequency. And so this is where this is going to come from. Think about if we're looking at a distribution and the distribution says, hey, 20% of the distribution is going to be green, and we're looking at 100 different elements, whatever we're looking at, we're just going to multiply that percentage times the sample size to get how many we would expect from our sample to be green. So the expected frequency, E, is just the sample size N times P. It's the same thing we were doing last time when we did X equals N times P. That same idea, that's how many we would expect to see in each category. Now, the value chi-square that they're going to come up with, the way you do that is you look at how many you would observe in any distribution minus what you would expect. And then what we're going to do is we're going to square those to make them all positive, add them up, divided by E. Now, we should put a bracket here because it's the observed minus the expected squared divided by the expected, and then we add all those up. So it's not just adding up the observed minus the expected squared. Okay, so that's how they calculate this chi-squared number. Again, we're not going to have to actually calculate it because we're going to be using StatCrunch. It's going to calculate all the numbers for us. But I want you to know where that number comes from, what it represents. So it has to do with the difference from what we observe minus what we expect. So if we observe exactly what we would expect, we're going to get a number of 0 there. And remember, chi-squared starts at 0. So the further chi-squared is from 0, the bigger the number we get, the more the distribution's not going to be what we expected it to be. Okay, so that's the idea. And let's just jump in and do a couple problems. So let me jump in here. I've already pulled up problem 3. Let's take a look. It says the distribution and the observed frequencies of the values of a variable from a simple random sample of the population are provided below. Use the chi-squared goodness of fit test to decide at the specified significance level whether the distribution of the variable differs from the given distribution. So we're going to do this. After we do this one, we're okay in this problem as far as the assumptions go, but I'll tell you the assumptions are before we do the next test. So we'll assume that they're okay right now, but we'll talk about them in the next problem. So determine the null and alternative hypothesis. Well, here's how we start. Let's kind of write this out this way. So the null hypothesis, the idea is that the distribution is going to be the same as what we would expect it to be. So the distribution of the variable is the same as the given distribution. Oops. The alternative is that there's a difference. So the distribution of the variable is different than the given distribution. Okay, so as always, we assume that things haven't changed, and then we look to see if they have changed. So when we look here and we look at our options, let's see, A says null hypothesis, distribution of the variable differs from the normal distribution. That's not what we're looking at. B, the distribution of the variable differs from the given distribution. Well, that's the alternative hypothesis, so B can't be right. C says the expected frequencies are all equal to 5. That has to do with the assumptions we'll talk about in a minute. So I'm guessing it's D, since none of the other ones are correct. The distribution of the variable is the same as the given distribution. That's true. And the alternative hypothesis, the distribution of the variable differs from the given distribution. So that's where we're going here. Now, let's actually go and do the test. So let me clear all this out, and we're going to run the test. So now notice when it says distribution, so here's what they're saying. We expect whatever this first category is, there's going to be 20% in the first category, 20% in the second category, 10% in the third, 30% in the fourth, and 20% in the fifth. What we actually saw was we saw 10 of our sample were in the first category, 2 in the second, 5 in the third, etc. And so we're going to say, hey, do those observed frequencies match that distribution that they told us, or is there something else going on here? So let's open this up in StatCrunch. We'll get all our data in there. Could not find data. Let's try that again. Okay, so there's our frequency, there's our distribution. So what we do is we go into stat all the way down to goodness of fit, and we're doing the chi-squared test. So it says, where's the observed data? Well, the observed data is your frequency. So pick that one. And what's your expected? Well, there's two options. Either they give you the distribution, or if we expect them all to be the same, we would click all cells in equal proportion. So we expect to be what the distribution is. And that's all we do, compute. So it tells us, oh, here's the observed. We expected 10. We observed 2 of these. We would expect 10 of those also, because remember, we expect 20% of the distribution. So they give us each of those, but what we really care about is my chi-square number and my p-value. So let's jot those down. So let's see. So chi-squared is equal to 10.267, and my p-value is equal to 0.0362. All right, from there we can just go and answer the question. So let's go back to our problem. It says, first of all, what is chi-squared? Well, that was easy enough. So chi-squared to 3 decimal places, 10.267. All right, what's the p-value to 3 places? 0.036. All right, that's good. Now, before I go from that, just so we have room, let's go ahead and answer the question. Now, notice they said up here, the significance level was 0.10. That's my alpha. So my p-value, I'm seeing if that's less than or equal to 0.10, which was my alpha. It is less because this is 3.6% versus 10%. So since my p-value is less than alpha, I reject the null hypothesis, which I had stated the distribution is the same. I'm rejecting that, saying I don't think it is. Let's go with the alternative, which says, oh, it looks like the distribution of the variable differs. So we're going to answer yes. Let's state it more in their terminology. The data provides sufficient evidence to say that the distribution of the variable differs from the given distribution. All right, so I never checked my answer on this one. So let's check my answer, make sure my p-value is right, which it is. Does the data provide sufficient evidence that the distribution of the variable differs from the given distribution? Well, remember, we rejected the null hypothesis, so we say yes, it does appear. So yes, because there is not, no. Yes, because there is sufficient evidence to reject the null hypothesis. All right, and so that was it. So that was number 3. Number 4, notice, is going to be very similar. Let's jump to number 5 as another example. A researcher drilled a hole in a die and filled it with a lead weight. So think about rolling dice. We've got a single die, 6-sided. The researcher drilled a hole and filled it with a lead weight, then proceeded to roll it 190 times. The observed frequencies for the outcomes of 1, 2, 3, 4, 5, and 6 respectively are, and they tell us what the observed outcomes were. Use a 0.05 significance level to test the claim that the outcomes are not equally likely. So this time we expect them to be equally likely. That's going to be our null hypothesis because we're rolling a die. We expect all 6 sides to come up evenly if it's what we call a fair die. Well, he put a lead in there to try to get it to come up on some of the sides more often than what would be equally likely. And so we're trying to see if that is actually happening. So let me first, I'm going to jot down what the assumptions are. And in fact, I'm going to go back. Let's go back real quickly and do that. And then we can come back here and check the assumptions. I'm going to go back to my note page and we'll jot down the assumptions there. It's probably a cleaner place to do that. Okay, so I've got all this. Let me clear from that and we'll go back up here. Okay. So let's see, here's my assumptions. Assumptions for chi-squared goodness of fit test. I guess I don't need a line there. For the chi-squared goodness of fit test. All right, here they are. 1, this probably won't surprise you. It has to be a simple random sample. All of the hypothesis tests we've had up to now have been simple random samples. 2, all of the expected frequencies must be greater than or equal to 1. So we can't have an expected frequency less than 1. Now, before we were saying all the expected frequencies had to be at least 5. Here they're saying, well, we've got multiple categories. We need at least 1 in each of the categories, but no more than 20% of the categories can be less than or equal to 5. Rephrase, can be less than 5. So no more than 20% of expected values. Maybe less than 5. All right, so those are the 3. Simple random sample like always. We have to have at least an expected frequency of 1 for all the categories. And then we can, even if we have one that's less than 5, that's okay, but we can't have more than 20% less than 5. Okay, so let's go back and we'll verify on this problem whether or not that's the case. So let's see. So what we have here is they're rolling, you rolled the die 190 times, so that's going to be a simple random sample because there's nothing that can come up in that to make that not a simple random sample, as long as he's just taking all 190 of the rolls. Now, the observed frequencies, remember, they'll have to be at least 1. Well, here's the observed frequencies right here. They're definitely all at least 1. And no more than 20%, well, 20% would be 1 out of 5. So we can't have more than 1 of these be less than 5. They're all greater than 5, so we're okay again. So if we think back to the greater than or equal to 5 that we had before, it's still that, although we could have 1 that's less than 1 out of every 5 could be less than 5 as long as it's at least 1. But we're okay here. So that checked those really quickly and really well. Okay, so now let's go in, we'll answer the question. Does it appear that the loaded die behaves differently than a fair die? Okay, so the null hypothesis, all outcomes are equally likely. That would make it a fair die. it's a fair die. The alternative, they're not all coming out equally likely. Not all outcomes are equally likely. In other words, it's a loaded die. All right, so let's see. At least one of the probabilities is different than the others. Well, that would be what I wrote as the alternative hypothesis. That's another way of stating that, but that's not the null. All outcomes are equally likely, okay, and at least one of the probabilities different than the others. That's the same thing as they're not all the same, is meaning at least one is different. So B is good. Let's see these. All frequencies are less than 5. That's an assumption. Obviously, it's not true in this case anyway, and all frequencies are equal to 5 or less than 5. That's not an alternative hypothesis. So we'll check this one out. We're good there. Compute chi-squared. So let's go here. The only difference here is when I go into StatCrunch, I was trying to find it. Data could not be found. These guys are killing me. We'll try this up to 3 times. If it doesn't work, we'll have to enter it ourselves. Let's try one more time. And before I do it, I'm going to take a picture of these numbers because we'll input them ourselves if we have to. Let's see. All right, so I just took a picture. Let's try it one last time. And no such luck. Okay, so here's what I'm going to do. I'm going to input this data. And this could happen periodically. So let's say we'll call this, and I'm going to call it something so I know what it is. Let's just call this observed, because that's what we're talking about. Well, here are the observed numbers: 25, 32, 36, 39. I'm just hitting enter in between each of these, by the way. 23, 35. So those are my observed numbers. Remember, these were all equally likely. If we wanted to put something here like the die, what we got on the roll, we'll even call it die roll. It sounds fancy. I could come here and say, oh, that was a 1, 2, 3, 4, 5. What didn't work too well, did it? 1, 2, 3, 4, 5, 6. So this is what I got on the roll. That was the observed, but the roll has nothing to do with anything per se. I mean, it could be a die that wasn't numbered 1 through 6. That could just be 6 different colors or whatever we're looking at. It's the observed. We expect these to be equally likely. So we're not going to use that 1 through 6 at all. So now when I go and I do stat, goodness of fit, chi-square test, the observed column was what we call observed. That's all I do. And then I say, oh, all cells are in equal proportion. Don't put in the 1 through 6. That's going to throw you off completely. So I expect them all to be the same. And now I compute. We see what we get. We've got a nice large chi-squared number. Let's write that down. Chi-squared. I don't know why I'm spelling this out. Chi-squared. 6.421. Now, if they go to another decimal, it's another 1. I don't think they do. I think they just went 3. Notice the expected, 31.67 is how many we would expect for every single outcome if they were equally likely, is what that says. My p-value is equal to 0.2674. We're going to compare that to whatever our alpha is, and we'll plug that in shortly. So let's go back to the problem, since I forgot what alpha was. They tell me right here, alpha is 0.05. Let's plug that in. Let's finish our hypothesis test. Now notice on the left, the p-value, that's 26.74%. Well, that's not less than or equal to 5%. So if it's not less, we do not reject the null hypothesis. And so if I can't reject it, it might be the case that all the outcomes are equally likely. So I say no. The data is not sufficient to show that at least one probability is different than the others. So we can't show statistically that it's a loaded die. We say, you drilled a hole and put a lead weight in there, but it's not clear that it's behaving any differently than a regular fair die. All right, so let's go answer all these. So my chi-squared value to 2 decimal places, 6.42. My p-value to 3 decimal places, 0.267. And then we answer our question, does it appear the loaded die behaves differently than a regular die? We're gonna have to say no, the data wasn't sufficient. No, because there is sufficient data to reject. No, there was not. No, because there's not sufficient evidence to reject the null hypothesis. If you're still having trouble with the p-value and understanding the p-value when you reject, when you don't, go into YouTube if you're not there already. Check my video on p-values. It's a really short video, and that's all I'm explaining. There's p-values. I think that'll help you quite a bit. But let's check this. Got the right answer. We can go to the next question. Now you'll see a problem 6 up here, but if I go to the next question, it's going to say, oh, your instructor already threw that out. Notice that came from 13.3. Again, that was a contingency table problem. We did those back in chapter 4. We don't need to do them again. So with that being said, that's the end of this chapter. Keep at it. Don't get discouraged. Lots and lots of hypothesis testing, but the more you do, obviously, the better and better you get. So with that, I'm going to clear this off. I will talk to you soon, and just keep going. You're going to get through this, and don't get discouraged.